Welcome to another video of embeddedblockchain.com. If you are new to this channel, I hope you enjoy our videos, and don't forget to hit the like button and the subscribe button. If you are not new to this channel, then welcome back and don't forget to hit the like button. Visit our page at embeddedblockchain.com, where you can find courses to get the education you need to be successful in this new digital era. In this section we will study a little history about computers and what they are. A computer is a device that can be programmed to perform specific tasks. You usually write software for the computer and the computer executes the software. A computer usually stores, processes, and displays data. Charles Babbage was probably the first to develop a computer. He is considered the father of computers. Babbage is credited with inventing the first mechanical computer. He was born in December 26, 1791 and died in October 18, 1871. The first computer built was probably the Eniac, a project built for the military. Most of the innovative technology we use today was developed for the military, then it was released for the world to use. Housed within 49-foot-tall cabinets, the machine contained 17,468 vacuum tubes along with 70,000 resistors, 10,000 capacitors, 1,500 relays, 6,000 manual switches, and 5 million soldered joints. Its dimensions covered 1,800 square feet. The first computers were huge in size. IBM was one of the first to build a personal computer, and was one of the first to launch a desktop computer which you could use at home. Apple was also one of the first to develop personal computers with the Macintosh. These computers do not compare to the ones we use today. Even your phone has more processing power than these computers. But they were considered very powerful at the time. Desktop computers are probably the first type of computer you started to use. This computer usually has a display, board, mouse and a cabinet. As its name implies, this computer is meant to be used on a desk. These are usually used at home or in an office. Mainframe computers are used for processing big data. Mainframes are usually very big computers used in data centers. Servers are typically used for cloud computing. If you ever hosted a website of your own, it was probably hosted in a server. Almost all websites you visit in the internet are stored in a server. This is the main purpose of this computer: to server up the information to other computers on a network. Nowadays, cloud computing has become very popular. One example is Amazon Web Services. They offer software as a service in the internet. The software they offer is run in servers. Microcomputers are also becoming very popular nowadays. With the rise of the Internet of Things, microcomputers will gain a lot of popularity. One example is the Raspberry Pi and the Arduino computers. These computers are becoming more popular in schools and prototype development. These are great for proof of concept. Mobile computers are probably the most computers used nowadays. I bet you have one smartphone that you use to communicate. Nowadays phones are more than just for making phone calls. They are basically computers that can run all types of programs. Wearable gadgets are another example of computers. These are usually devices you can wear for personal use, like a smartwatch, intelligent shirt. Wearable gadgets are a technology that is about to change the way we live. Technology will no longer be an external thing, it will be a part of us. In this lesson you will learn the basics about microcontrollers and their architecture. We start by asking the question: what is a microcontroller? You may have heard this word a lot when people talk about technology and embedded systems. Let's explore what is a microcontroller and the various examples to get a better understanding of it. A microcontroller is the kind of miniature computer that you can find in all kinds of devices nowadays. A list of devices that contain microcontrollers are: smartphones, microwaves, smart TVs, stereos, cars, digital scales, toys and games, washing machine, exercise equipment, remote controls, smart watches. The most used ones nowadays are definitely smartphones and smart watches. You probably have one of those and you have seen what they can do, but those are not the only devices that use a microcontroller. Microwaves have one to program the different cooking times and power level. Washing machines have a microcontroller that controls the washing cycle and time, also the water level inside the machine. So you see how microcontrollers are widely used nowadays, and are becoming an important part of our lives. The smartphone we use every day is probably the one that is having the biggest impact in our lives. Nowadays there is an app for almost everything. It basically has more computing power than a computer in the 90s. Another application is the smartwatch, which works in a similar way as the smartphone but has a different style. You can install apps, you can monitor physical activity such as heart rate, steps, etc. These type of portable devices are becoming extremely popular nowadays and are gaining adoption very fast. Another typical example is virtual reality. Virtual reality is becoming more and more popular also. These devices usually have high-performance microcontrollers or processors to run all the real-life graphics. Nowadays microcontrollers are part of our lives. We use them every day, sometimes without realizing it. When we text someone with our smartphone, when we turn on the TV, when we are driving the car, etc. Microcontrollers are also used in scientific, high technology, and aerospace projects. Airplanes, missiles, satellites. In the future almost every device will be using a microcontroller. This will allow the device to become smart and make decisions to make our life easier. Understanding microcontrollers nowadays is very important if you want to get into the embedded development industry. This industry has been growing significantly for the last 10 years and will keep growing in the future. To better understand the expression embedded microcomputer system, consider each word separately. Embedded means hidden inside so one can't see it. System means multiple components interface together for a common purpose. Micro means small. Processor. A computer contains a processor. Hence the word microprocessor. In this section we will be discussing what systems are. What is a system? In order to understand better how a microcontroller works, it is very important to understand a system. A system has inputs. Performs a process, usually the process wastes some kind of energy such as heat, noise, etc. and delivers an output. A system has inputs and outputs and must do something. If the system does nothing then the system is useless. When the system does something, it is said to do a process. Usually when this process is carried out, there is a waste of energy. A process can be anything, like cleaning dishes, vacuum floor, process data, capture image, etc. Let's take a look at a few examples of systems that we use in our everyday life. The washing machine is an example of a system. It has inputs such as the voltage that we supply, the clothes we want to wash, the soap, It performs a process and delivers an output, which is the movement it produces to wash the clothes. And it also wastes energy. This energy is usually manifested in the form of noise and heat, which we can hear and feel when we are washing our clothes. For now, focus only on what a process is. Right now we are not talking about microcontrollers. Let's take a look at another type of system. The car is another example of system. It has inputs such as gas, oil, water. It performs a process and delivers an output, the movement it produces to transport us. And it wastes energy. The noise and gases it delivers are considered waste. We can often hear the noise and smell all those gases produced by the cars. This is considered the waste energy. Now let's take a look at some terms that you will often find in the embedded world. Now, the previous systems you saw were not exactly embedded systems. One term you will hear is microcontroller-based system or microprocessor-based system. A smartwatch is a microcontroller-based system. It contains a microcontroller inside that runs all the programs installed in it. The inputs are the touches given by the user. The process is the processing of the applications in order to show the information to the user. The output is the graphical interface that we see on the screen. The waste is usually heat. All this information is processed by the microcontroller and displays all those icons and text that you see on the display. Another term is microcomputer. The microprocessor-based systems that happens to be used as a computer are called microcomputers. Formerly we had what we called PCs, which had a CPU, memory, storage and peripherals. Microcomputers are becoming very popular in the embedded world. Since everything is becoming about portable devices, we want something that is small and portable. These microcomputers, although they are very small, they are very powerful and can process huge amount of data. The Arduino and Raspberry Pi are becoming extremely popular among developers who want to enter the embedded world. There are other microcomputers less common that are also available, such as BeagleBone, which is very similar to Raspberry Pi, but it has less support from the community. Our car, which is supported by Renesas. This is very common among developers entering the automotive industry development. Microcontroller. This is a complete microprocessor-based control system built onto a single chip. It is small and convenient but doesn't do anything on its own. It needs external components in order to be useful. A microcontroller is another type of small computer. The difference is that it has all the required parts inside. It doesn't need memory or hard disk connected to it in order to work. Everything is already inside it. Common vendors for microcontrollers are NXP, Texas Instrument, Renesas, Atmel Microchip. In this section you will learn the binary system and why it is used in computers. You may be wondering why machines use binary. Why not the same decimal numbers we use every day? Machines use binary system, they only count 1 and 0. Microprocessors do not use the numerical system we use, they use the binary counting system. So this is one of the biggest questions people ask is, why binary? Why only use 2 values and not 10 like us, or at least 3 or 4? Let's analyze this for a moment. Almost all computers work with 5 volts. Some of them might work with 3.3 volts, but in general they use 5 volts. So if we want to make a numerical system, it would have to be from the range 0 volts to 5 volts. It could not be outside the voltage range of our microcontroller. This is a very important concept that we have to understand when we talk about computers and microcontrollers. Since most microcontrollers work with 5 volts, almost every electronic device will use this voltage level. Now, just for curiosity, let's see what would happen if computers used a decimal system just like us humans. Okay, so in order to use a decimal system we need to assign a value of voltage to each number. People use decimal numeric system. We count from 0 to 9. In order to do this with our microcontroller, we assign a value to each number, as shown in the table. 0 volts equals 0. 0.5 volts equals 1. 1 volt equals 2. And so on. Now we humans do addition like this, 2 plus 2 equals 4. Our microcontroller would need to add the two equivalents. 1 volt plus 1 volt equals 2 volts. As humans we would add 2 plus 2 equals 4. Our computer would do this operation like this. 1 volt plus 1 volt equals 2 volts. So now we have a decimal system implemented in our microcontroller. Depending on the numbers we want to use is the level of voltage that the microcontroller would use. Simple, right? Well, not so fast. In the graph we can see this operation. Now this looks perfect in the ideal world, but in the real world things are not so perfect. Let's take a look at how things would be in our real world. In the real world the signal would look pretty much like this. In the real world, embedded devices receive a lot of noise, due to static from the body, due electromagnetic signals in the air. Embedded devices are very sensitive to this noise signals and affect the voltage with which they operate. If we take samples as shown in the graph, then we would get 1.2 volts plus 1.4 volts equals 2.6 volts. Our computer would be giving us a result of 2.6 volts which corresponds to number 5. In other words, according to our computer 2 plus 2 equals 5. Oops, looks like our plane just crashed. You see how noise can affect your calculations, when you have very little range of operation. So why don't we just increase the operating voltage to say, 10 volts, or 100 volts? The higher the supply voltage the higher our range of operation, hence the less likely it is that electrical noise would be a problem. This is true, but the effect of increasing the supply voltage would be to require thicker insulation and would increase the physical size of the microprocessor and reduce its speed. In other words, our microcontrollers become less efficient as we increase the voltage. Imagine a microcontroller the size of a brick, not quite what we are used to see nowadays with little devices becoming more powerful. You don't want to be carrying a brick-sized smartwatch in your hand operating at 100 volts. Trust me. So here is where we need to consider another solution instead of increasing the voltage. Another solution is to reduce the number of digits that we work with. If we reduce the number of digits, then a wider voltage range can be used for each value and the errors due to noise are likely to occur less often. We have chosen to use only 2 digits, 0 and 1, to provide the maximum degree of reliability. A further improvement is to provide a safety zone between each voltage. By doing this, even with noise our margin for error is greater and we don't have to use a high voltage which would cause our microcontroller to be huge in size due to the power consumed. We can say that everything above 2.5 volts is 1. And everything below 2.5 volts is 0. So now as you see in the graph, the noise is not crossing the 2.5 volts line that we have set as the limit. This is very helpful for our calculations since now we can inject 5 volts or 0 volts and we can interpret accordingly. No more miscalculations. Let's analyze how we humans count in decimal and compare it to how computers count in binary. You probably already know this, but I'll explain to you how the decimal system works and then compare it to binary system. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. We have reached the maximum number of digits in our decimal system. If we want to keep counting, what we do is carry 1 and start over. As you can see, we added the number 1 and started counting again. Let's do it one more time. Now we have added number 2 and started counting again. This process repeats over and over again, increasing the number of digits. We can use as many digits as we want. We can count in any base that we want. We saw how humans count in decimal, now let's see how computers would count in binary. Counting follows the same pattern as we have seen in the denary system. We use up the digits then start again. 0. 1. That's it. In binary there are only 2 digits. But we want to keep counting, so let's keep counting in binary. Let's count in binary. The binary counting are. So you see how the same pattern is followed. Every time we want to start another round of counting, we add an extra digit and start counting all over again. In the embedded, microprocessor world, it is important that you learn how to convert from decimal to binary and vice versa. You don't need to do it by hand, you can use a program or calculator to make it faster. We will not focus on conversion in this course. Since nowadays you can find in Google many websites that do binary conversion for you, you just need to enter your binary digits and they will convert it for you. It is also very important that you learn to convert from binary to hexadecimal, since hexadecimal is the most used system when working with micros. Working with binary is too hard for humans, so we convert it to hexadecimal to make it easier. We recommend using a calculator when converting values. Remember that we can use any counting system that we want. We already saw how to count in decimal and binary. Now what if we had 16 digits to choose from? How would that be? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Since we ran out of numbers, we will use letters A, B, C, D, E, F. Now we have successfully counted in hexadecimal-based system, meaning that it has 16 digits to choose from when counting. Now let's keep counting using the same methodology as before. 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 1A, 1B, 1C, 1D, 1E, 1F. We can keep counting just as we did before. Now we have a more broad range of digits for our counting system. The hexadecimal system is very important in the embedded world because it is widely used when programming the microcontrollers. Later we will see how this system is used when we start programming microcontrollers. An example of a hexadecimal number is: you probably have seen such numbers in the internet or addresses given for certain operations. This is a hexadecimal number and can easily be converted to binary or decimal. Now let's look at some terminology in the digital world. Bit. It is the most simple digit in a digital system. Can be 0 or 1. Nibble. A group of 4 bits handled as a single lump. It is half a byte. Byte. A byte is simply a collection of 8 bits. Whether they are ones or zeros or what their purpose is does not matter. Out of all these you probably have heard the word bit and byte a lot in the computer world. The term nibble is not used a lot, but it is important to know the terminology. A number of bits can be collected together to form a word. Unlike a byte, a word does not have a fixed number of bits in it. The length of the word or the number of bits in the word depends on the microprocessor being used. This term is also widely used in the embedded world and it doesn't have a fixed amount of digits. Later we will see why. For now just know that a word is greater than a byte and it is a collection of bits. Long word usually means twice the length of a normal word. There are also other terms like kilobyte, which is basically 1000 bytes. But it is not exactly 1000, it is more like 1024 bytes. This has to do with the fact that in binary we will not count exactly 1000 but 1024. A megabyte is equal to 1024 kilobytes. The same principle applies here. Other terms are gigabyte, which is equal to 1000 megabytes. This is probably the most common term nowadays in computers. Also the term terabyte, which is equal to 1000 gigabytes. These are very common terms when we talk about disk sizes in computers, or when downloading some file in the internet, we often hear these terms. In this section we will study the registers in the microcontroller. In order to understand registers we need to understand what a flip-flop is. Flip-flops are an array of logic gates put together. For now you just need to understand that a logic gate is made of transistors and a flip-flop is made of logic gates. The array is such that it follows a specific logic when you input values. Let's analyze the logic the flip-flop follows. The sequence of the events is: data is applied at the input. After one clock cycle, the data is stored inside the flip-flop. Data is available at the output after one clock cycle. What is the clock signal? The clock signal is used to tell the flip-flop that it is time to read the input. All microprocessors' operations are carefully timed by clock pulses. A register is just a collection of flip-flops. A flip-flop can only store one bit, so to handle 4 bits at a time, we would need 4 flip-flops and would refer to this as a 4-bit register. In this image you can see a 4-bit register using flip-flop. Usually registers are designed to read and write data using the same data bits. Internally they are designed to handle voltage in both directions, in and out. Clock, this signal is used to synchronize the reading and writing of the data bits. D0 to D3 are the data input. Q0 to Q3 are the data output. So whenever we put data in the D0 to D3 inputs and we get a clock pulse, the data is put into the Q0 to Q3. This is how we write to a register. Registers can get more robust, adding more functionality. In this example we see a register with clock used to synchronize the inputs. Enable input used to enable or disable the register. Usually a register must be enabled before we start using it. And finally read/write input, used to write data to the register or to read data from the register. The bits are the data that is being used. The size of the bits depends on the microcontroller being used. There are 8-bit microcontroller, 16-bit microcontrollers and 32-bit microcontrollers. The most modern ones now have up to 64 bits. This depends on the manufacturer. Registers are storage areas inside the microprocessor. Almost the whole of the microprocessor is made of registers. They store the data that is going to be used, they store the instructions that are to be used, and they store the results obtained. Nearly all registers involve tri-state buffers to control the direction of data flow. Each register has an address inside the microcontroller. This is how the microcontroller knows which register to read from and to write to. Register 1 has address 01. Register 2 has address 02. And so on. This is called a bank of registers. Each register has an address assigned and each register stores data. You will later see that in microcontrollers is all about addresses to access memory and peripherals. The function of a memory is to store information, almost the same as we said for the register. Generally, a register lives within the microprocessor and stores small quantities of data for immediate use, and it can do useful little tricks like shift and rotate. A memory is designed for bulk storage of data, but that is all it can do. There are mainly 3 types of memory: RAM, ROM and a hybrid combination of the two. RAM is used to store data temporarily. Data is lost when power is off. ROM is used to store data even after power is off. You will later see the types of memories. For now understand these 2 types of memory: temporary and permanent. In this scenario, temporary means data will be lost if you disconnect the power from the microcontroller. Permanent means data will remain even after power is removed. It does not mean that it cannot be changed, it just means it stays there until you decide to modify it. The following is a list of types of RAM used in today's computers. You probably have heard a few of them. When you buy a computer or laptop, you probably hear that it has 4 GB of RAM and the type of memory is DDR or SDR. Just know that each type has different speeds, different type of design, but they basically do the same: they store data temporarily. The following is a list of types of ROM used in today's computers. You probably haven't heard these types of memories in computers because they are mainly used for microcontrollers. This is what the microcontroller uses to store the program. The microcontroller doesn't have a hard disk like the laptop where you store your programs. Instead, it uses ROM memory. The most common type of ROM memory nowadays is flash. The most basic microprocessor system consists of memory, CPU and a clock. Program memory, this is where the program is stored, instructions for the CPU. CPU, central processor unit, this is the block that processes the instructions and does the process. Clock, this is needed to tell the CPU to execute the next instruction. To keep the whole system synchronized. The clock is very important since it determines the speed at which the instruction will be executed. You've probably heard a lot about gigahertz when you buy a laptop. This is the speed of the computer basically, the higher the hertz the faster the computer. A microcontroller must be programmed. This means that it must be provided with a series of instructions to be followed. These instructions must be stored in ROM memory. Or as we discussed previously in flash memory. Which is the most common nowadays. Remember that ROM memory stores data permanently. Remember that in our basic register we had a clock input, and that inputs were read or written whenever a clock pulse was received? A clock circuit controls the operation of the microprocessor. This produces a series of voltage pulses like a ticking clock. The whole system runs sequentially, doing the required jobs one after the other. One step completed for each tick of the clock system. A 200 MHz clock pulse is shown in the image below. 200 MHz means that it produces 200 million pulses per second. Basically every pulse in the clock will tell the CPU to execute the next instruction. So the more pulses per second, the more instructions per second that are executed. In a microprocessor-based system we have two main buses, the data bus, the address bus. The data bus is a two-way bus carrying data around the system. Information going into the microprocessor and results coming out. The address bus carries addresses and is a one-way bus from the microprocessor to the memory or other devices. Remember that microprocessors have bank of registers where data is stored, well this data is accessed using the buses. Also remember that each register has an address assigned, so we need to know the address and we need to know the data inside the register. This is why we have two buses. In our basic microprocessor system we saw how we can interface with external circuits. This gives option to add extra interfaces to our microprocessor. One of the most important interfaces is the input/output interface. Here you can see an improved microprocessor-based system, where we include an input/output controller. This allows the developers to interact with real-world hardware such as LCDs, LEDs, buttons. Later we will see the blinky example where we will turn on and off an LED, this is done using the input-out peripheral. The concept of peripherals is important to understand because this is what makes different a microcontroller from microprocessor. The microcontroller is basically a complete system that you can program and control external devices. The microprocessor is just the computing unit but it doesn't have any peripherals, this is something you have to add separately. Apart from the most minimal system, some RAM memory is needed. Even if the microcontroller is controlling garage door, we still need a way to change the values of the outputs, or do some calculations without affecting the original software, so some RAM must be added. Here we show you a complete microcontroller system. It includes RAM to store temporary data and to be able to vary that data while our system is working, ROM memory to store our instructions, a clock to indicate when to execute the following instruction and an input/output controller. Later we will see why RAM memory is so important. For now understand that when the system is operating it needs to be able to change memory data according to external changes. For example, if we are monitoring temperature, the microcontroller will read one value now and later the temperature may vary, so it needs to update that value accordingly. This is possible with RAM memory. You can change the data at any time easily. Now, one aspect microprocessor-based system is storage capacity. This is defined by the number of lines. The more capacity is needed, the more lines we need. Remember the binary system and how computers count. The maximum number the computer can count depends on the number of bits or lines. With 1 bit we can count 2 times. With 2 bits we can count 4 times. If we keep adding more lines, we will keep doubling the capacity of our storage. In the following table we show you the capacity according to the number of lines. As we can see, if we have 10 lines or bits in our registers, we can store up to 1024 bits or 1 kilobit of data. This is what we mean when we say 8-bit microcontroller or 16-bit microcontroller. The more bits, the more capacity to store data. Microprocessors are central components of almost all digital systems, because combinations of hardware and software are used to solve design problems. A computer is formed by combining a microprocessor with a mix of certain basic elements and customized logic. Computer architecture is fundamental to the design of digital systems. Understanding how a basic computer is designed enables a digital system to take shape by using a microprocessor as a central control element. The microprocessor, often called a microprocessor unit, MPU, or central processing unit, CPU, contains logic to step through an algorithm, called a program, that has been stored in the computer's program memory. Programs are composed of many very simple individual operations, called instructions, that specify in exact detail how the microprocessor should carry out an algorithm. A microprocessor connects to devices such as memory and I/O via data and address buses. In the following diagram you can see a basic computer architecture, which consists of the microprocessor, ROM memory, RAM memory and I/O devices. There are two major architectures in the computer world. The Harvard architecture. In the Harvard architecture, the volatile, data, and non-volatile, program, memories are treated as separate systems, each with its own address and data bus. Many microcontrollers use this architecture, including microchip PICs, the Intel 8051 and descendants, and the ARM9. The principal advantage is efficiency. There is only a single memory system in the von Neumann or Princeton architecture. This means that only one set of addresses covers both the volatile and non-volatile memories. The memory map, which shows the addresses at which each type of memory is located, becomes particularly important. ARM Cortex architectures. This type of architecture is becoming extremely popular nowadays. And it is the type of architecture used in your phone, your car, smart TV and many more devices. ARM processor using a Harvard architecture for the core. ARM provides an architecture where manufacturers can build upon. ARM does not manufacture microcontrollers. What it does is, it builds the core architecture so that silicon manufacturers can add their interfaces and sell their own microcontrollers. ARM can be either von Neumann or Harvard. The ARM processors are gaining a lot of popularity. They are widely used in embedded devices. With the rise of the IoT embedded devices, they are being rapidly adopted. ARM processors are found in numerous market segments, including networking, automotive, mobile and consumer devices, mass storage, and imaging. Within each segment, ARM processors can be found in multiple applications. Application processors, Cortex-A, high-end processors for mobile computing. Real-time processors, Cortex-R. Very high-performance processors for real-time applications. Microcontroller processors, Cortex-M. Very popular in the embedded systems market. ARM processors can be found on almost every device nowadays, including smartphones, tablets, smartwatches, remote controls, smart refrigerators, games, etc. In this course you will learn to program an ARM microcontroller. Since this is becoming the standard nowadays and has a bright future ahead with the rise of the machines. We will now study the assembly language. This language is very important to understand, although is not very used nowadays, but it helps you get a better idea of how computers operate at low level. We know that computers work with binary systems, they only count 0 and 1. This can also be represented with hexadecimal system. In this picture we see the registers of microcontroller and their data. These are the addresses of the registers. And this is the data contained inside the registers. If you wanted to program the microcontroller you would need to write these numbers inside the registers. Can you understand what it says? For us humans this is very difficult to understand. One common example is the move instruction. Here we have the three languages, machine, assembly and human. The three basically mean the same. Put 100 into R1. R1 is a register inside the microcontroller. We can see how the register 1 was modified after we executed the instruction. This is more comprehensible way for us to understand what the machine is doing instead of seeing 0 and 1. If we had to program the microcontroller in machine code it would be very difficult for us to remember what each number means, so we use assembly language. These are some examples of assembly language and machine language. The assembly language is not used a lot nowadays, it is only used for interpretation of the program, to understand what the micro is doing. We will later see how we can debug SW issues by looking at assembly language. A programmer can think of an ARM core as functional units connected by data buses. Data enters the processor core through the data bus. The data may be an instruction to execute or a data item. We show an example of an ARM architecture. The ARM has a total of 18 active registers, 16 data registers and 2 processor status registers. Remember how the microcontroller is made of a bank of registers? These are the main registers in the ARM processor. Among the data registers we have, R13, SP, stack pointer, points to the top element of the stack. There are 2 stack pointers, main stack pointer, MSP, and process stack pointer, PSP. R14, LR, link register, is used to store the return location for functions. R15, PC, program counter, points to the next instruction to be fetched from memory. These are highlighted in blue. We will talk about these registers more. Each register serves a purpose. We will describe the generic program status register, which is standard in the ARM processors. Each bit means something in the status registers. N, negative, this bit will be 1 when the result of the operation we perform is negative. Example, we subtract 3 from 2, we would get a negative result. Z, 0, this bit is set to 1 when the result of the operation is 0. C, carry, this bit is set when the result of the operation is greater than 0. V, overflow, if the result is greater than 31 bits, this bit is set to 1. Q, indicates saturation. T, bit indicates the processor is in thumb state. Later we will see the thumb and ARM modes. Mode, indicates the mode of the processor. The mode state has 7 possible values. We describe some of the states. User mode is used in the normal state, This is when the processor is executing a program normally. IRQ state is used when the processor enters an interrupt mode. Supervisor is usually used for the operating system. System is usually used when the operating system is running privileged tasks. When the processor is executing in certain modes, not all registers are available. Depending on the state are the registers available. The processor has 37 registers in total, but 20 of them are hidden from a program at different times. These are called banked registers. Depending on the mode the processor is in, certain registers will be visible to the processor. This picture illustrates which registers are available in each mode. The colored ones are available in each of the modes indicated. The TM4C microcontroller, which is the one we will be using in this course, has a Cortex-M4F core. This architecture is defined by ARM. As we saw previously, this is what ARM provides to Texas Instrument. It contains the main logic for a microcontroller to do all computing tasks. Texas Instruments adds the peripherals which are used to interact with external hardware. This is usually how microcontroller manufacturers use ARM architecture to manufacture their microcontrollers. As an extra example, we show the KINETIS K70 by Freescale, now NXP. It also has a Cortex-M4 ARM architecture. And Freescale added peripherals to interact with external hardware. The most important thing to understand from all of this is that ARM devices have a common architecture. The code is backwards compatible. This allows code portability, that is, we can write code for one processor and easily port it to another ARM processor. This is very convenient and is one of the reasons ARM is becoming very popular. Another reason is performance. ARM processors are very efficient and can execute large amount of data very efficiently. PO stands for General Purpose Input/Output. In fact, most of the pins in a typical microcontroller are PO pins except for some special pins. Basically almost all pins in the microcontroller are inputs and outputs. In the diagram we show picture of the TM4C microcontroller. Each pin can be configured for different functionalities, as we will see later in the course, but basically you can configure them as inputs or outputs. Microcontrollers use the concept of a direction register to determine whether a pin is an input or an output. In this picture we illustrate the concept of input and output. It basically determines the direction of the current in the pin. A microcontroller often includes hardware functionalities, peripheral modules, like serial communication, which is very useful when we want to communicate two devices. We will see later how we can communicate our computer with the microcontroller using this peripheral. Timers. These are very useful for creating delays and counting. Digital I/O are very useful for turning on LEDs or turning on motors. Analog I/O are very useful for measuring analog signals such as temperature, light brightness, etc. GUI or LCD controllers are great for displaying information to the user in a graphical manner. Networking can be used to communicate devices connected to each other, such as Ethernet. A digital input-output may seem very simple, we just turn on and off the signal and that's it, you might be thinking. But it's more complex than that. In this picture we show you one module of the I/O for the TM4C microcontroller. The TM4C microcontroller has 6 modules just like this one. This section of the register is used to control the data of the port. In the TM4C microcontroller we use these 2 registers to control the value of the pins. PO data is basically where we manipulate the pins. PO dir is where we configure the direction of the pin, whether is input or output. Of course we can only manipulate the data of the pins when they are configured as outputs. If they are configured as inputs, then we can only read the value they have. Port control provides some options to select the functions of the port. Remember how one pin can be used as digital input/output or as analog digital converter or PWM. The mode control is used in conjugation with port control to select the alternate function. Both blocks must be configured together in order to enable the alternate function in the pin. These registers control drive strength, open drain configuration, pull up and pull down resistors. These are very specific configurations for the port. Depending on the usage you are giving it, each application might have different configuration. Some ports have interrupt capabilities. You can configure the behavior of those interrupts in the interrupt control register. We will later see how an interrupt works. Interrupts are very useful when we want to monitor external events, such as the push of a button. In the real world, most data is represented by analog signals such as sound, temperature, light. We don't get digital signals in a real world. Everything is sound waves, light waves, it's all analog. In order to work and manipulate those signals, we need to convert them to digital signals because the microcontroller works with digital signals. We receive an analog signal, we put it through the ADC and we get a digital signal. The ADC achieves this by sampling the analog signal at different times. There are two parameters that control the conversion of the signal: sampling rate, quantization, number of samples taken per second. Sampling precision, resolution, the level of precision at the moment of capture. Even if we have high sampling rate, if we don't have good precision, the reading can be incorrect. Both are extremely important when using an ADC. All microcontrollers have an oscillator. Some are external, some are internal. This oscillator helps the microcontroller generate a clock signal. Most of the times you will see a quartz crystal being used as oscillator. Quartz crystal provide a stable frequency that they generate by nature. This frequency serves as a reference to generate a clock signal. A clock signal looks something like this, where one full cycle is called the period. An instruction is executed every cycle inside the microcontroller. Depending on the microcontroller, it could take 1, 2 or 3 cycles for one machine instruction to be executed. The clock is one of the most important parts of the microcontroller. The more cycles per second, the higher the frequency, and more instructions are executed per second. Here we show you the clock module of the TM4C from Texas Instrument. In this section we have the oscillators. You can choose from 4 different oscillators. Each oscillator provides a different frequency. And it also has different clock outputs. Each clock controls a different part of the microcontroller. Usually the system clock is the one that controls the CPU, the one that dictates the speed of the processor. You have probably heard the term gigahertz when you buy a laptop. This is basically referring to the speed of the processor, the speed at which the computer can execute instructions. A timer is basically a counter that can be configured to count up to a certain value and then restart counting again. All you do is configure a counter that will be restarting the count every time it reaches a maximum value. And you can configure that counter to set a flag or register every time it reaches the maximum value. In periodic mode, the timer continues counting after it reaches timeout. It merely clears the timeout flag of the timer and restarts. In periodic mode, the timer is counting up or down and restarting. It never stops until it is stopped by user code. In one-shot mode, timer stops counting after timeout. When we set an input, the timer starts counting. When the timer finishes counting, a flag or output is set. In input edge mode, we are basically capturing the value of the timer at that time. This is very useful when we want to measure how long a signal lasts or how often a signal is being triggered. In this lesson you will learn about UART, a very common protocol for transmitting data between microcontrollers. UART stands for Universal Asynchronous Receiver Transmitter. UART is a protocol for serial communication. It is called serial because all data is transmitted in the same line. We have the situation where two microcontrollers need to communicate with each other, and they need to understand each other. In order for the microcontrollers to understand each other, they need to speak the same language. This is the concept of a protocol, a language or a set of rules that both microcontrollers can follow. When the microcontroller transmits data, it has to send it in blocks. Each block will have a portion of data, and each block will follow the rules implied by the UART protocol. Each block consists of a start bit indicating where the block begins, then the data we want to transmit. Finally, a parity number and a stop bit indicating the block has ended. This way the microcontroller receiving the data will know where each block of data starts and ends. And will also know how to read the data inside the block. A serial bus consists of just two wires. One for sending data and another for receiving it. As such, serial devices should have two serial pins, the receiver, RX, and the transmitter, TX. It is worth noticing that one is the receiver of the other. Like everything in life, nothing is perfect. There are advantages and disadvantages in using the UART protocol. Two big advantages is that it only uses two wires, and it is a very well documented protocol. You can find plenty of documentation out there. Among the disadvantages are: it doesn't support multiple slaves or masters, only two devices can communicate. The size of data is only 9 bits. UART is a very popular protocol, but it's not the only one. There are more protocols out there that are newer, better and faster. Picking the right protocol is a tricky task. PWM is a modulation process. It is used for controlling the amplitude of digital signals in order to control devices and applications. The PWM creates a square signal which is switched on and off as shown in the image. The first concept we need to understand is the duty cycle. The duty cycle is the percentage of the on cycle with respect to the whole cycle. If the on cycle is 50% of the whole cycle, then we have a 50% duty cycle. If it is 75% of the whole cycle, then we have 75% duty cycle. We get the duty cycle by dividing the time in which the signal is high by the total time of the cycle. By doing this we are varying the power being delivered to the device. PWM is very useful because by varying the duty cycle of a digital signal, we are varying the power delivered to the device we are controlling. This way we can control motors, LEDs. We can vary the intensity of a LED. We can vary the speed of a motor. And so many other things.